Hey everybody, welcome back to the channel. I'm glad you're here for another video. Today we're going to be covering an interesting and honestly a bit of a complicated problem. We're looking for the value of alpha plus beta given that alpha and beta are real numbers such that the limit as x approaches 0 of 1 over x cubed of alpha over 2 of the integral from 0 to x of 1 over 1 minus t squared dt plus beta x cosine x is equal to 2. Like I mentioned, this problem is a bit involved, so if you feel the need to go back and watch a section again to make sure you understand everything, please do so. With that out of the way, let's get started. So the first thing I like to do when I evaluate limits is just substitute that limit in the expression given to see what I can figure out. Now here I wrote this limit as a quotient. You'll see why I did that in a moment. So we're just going to substitute 0 for x to see what we end up with. All right, in terms of the numerator, we're going to end with alpha over 2 times the integral from 0 to 0 of 1 over 1 minus t squared dt. But that's just going to equal 0 because then the upper and lower limits would be the same. They'd both be 0. In terms of the second term in the numerator, we have beta x cosine x. When you plug in 0 for x here, you're going to get 0 again. And then in the denominator, you have x cubed. Again, as x approaches 0, x cubed is just going to approach 0, which means that we have 0 over 0 here. Well, we can't divide by 0, and our limit is supposed to equal 2. What the heck is going on here? If you're familiar with limits and you've covered this in your Calculus 2 class, you know that this is an indeterminate form. 0 over 0 is one of the indeterminate forms. And when we have an indeterminate form, we need to use what's called L'Hopital's rule to simplify this. So with L'Hopital's rule, what we need to do is just take the derivative of the numerator and then take the derivative of the denominator. And that's going to give us our new expression to find the limit of. Now we're just going to find the derivative of the numerator and the derivative of the denominator in accordance to L'Hopital's rule. For the first term, we have the integral from 0 to x of 1 over 1 minus t squared dt. This is just going to become 1 over 1 minus x squared because of the fundamental theorem of calculus. We'll have alpha over 2 times 1 over 1 minus x squared. And like intuitively, the fundamental theorem of calculus tells us that essentially integration and differentiation are kind of opposites. They cancel each other out. So if you're differentiating an integral, such as the one we have here, you're going to end up with the integrand, the expression that you're integrating. So that's why we have 1 over 1 minus x squared here. Now, differentiating the second term in the numerator is going to leave us with 2 extra terms. And we're going to have to use a product rule here. So it's going to be the derivative of x times cosine x plus the derivative of cosine x times x. Okay, the derivative of x is 1, and this cosine x is going to stay the same. And then the derivative of cosine x is negative sine x. I'm going to change this plus to a minus. The x is going to stay the same. That means we end up with x sine x here. And in the denominator, well, differentiating that part is a lot simpler. This is just going to be 3x squared. And now we're going to try to evaluate this limit again to see what we end up with. Now we're just going to look at each term in the numerator and the denominator. I'll start with 1 over 1 minus x squared. As x approaches 0, this expression here is just going to be equal to alpha over 2 because this expression is going to approach 1. It's going to be equal to 1 as x approaches 0. That means we have alpha over 2. And then here, the limit as x approaches 0 of cosine x is 1. And since this other term here has an x, the limit as x approaches 0 is just going to be 0 here. That term is going to go away. That means that in this bracket, we just have beta. And in the denominator, this expression is going to approach 0 as x approaches 0. We end up with alpha over 2 plus beta is equal to 0. And according to the problem statement, this limit is supposed to be equal to 2. That means this is equal to 2. At this point, it looks like we really haven't made much progress here, but I want you to think closely about what alpha over 2 plus beta would have to be equal to. If alpha over 2 plus beta is non-zero, then this limit here would be undefined. Like, let's say that this numerator is 4. That means that we end up with the limit of x approaches 0 of 4 over 3x squared. But this is not defined. This doesn't exist. It's not equal to a finite number, which you can see more easily if you just look at a graph of this function here. So the only possibility, if alpha over 2 plus beta can't be non-zero, is that alpha over 2 plus beta is equal to 0. So in order for this limit to exist, we have to have another indeterminate form. I know that was a lot, so if you didn't quite understand that, please just watch the part of the video again and hopefully it makes more sense. I wrote here, if alpha over 2 plus beta is non-zero, then L would not exist. So alpha over 2 plus beta has to be 0, and we have another indeterminate form. Now this tells us two key pieces of information that will allow us to continue in this problem. And that is that alpha over 2 plus beta is equal to 0. In other words, that means that alpha plus 2 beta is equal to 0. Now we have this relation in terms of alpha and beta that will be useful for the rest of the problem. And this also tells us that since we have another indeterminate form, we need to apply L'Hopital's rule another time in order to figure out some more information. We do have one equation here, but we still need to know more in order to actually find the value of alpha plus beta. All right, now we're going to apply L'Hopital's rule to the expression that we got from differentiating the original limit. We're going to differentiate again. I've copied this expression from above. This limit is going to be equal to the limit as x approaches 0 of alpha over 2. Okay, and we're just going to follow the same process that we did in previous steps, just differentiating each term. There are a couple of ways you can differentiate 1 over 1 minus x squared here. You could use the quotient rule, but I would just use the chain rule. The outside function would be 1 over x. The inside function would be 1 minus x squared. So I'll just write d over dx of 1 over 1 minus x squared is equal to, again, this is so this is the same as 1 minus x squared to the negative first power, which is going to be negative 1 minus x squared to the negative second power times the derivative of 1 minus x squared, which is going to be negative 2x. And then once we simplify this, we get, negative times a negative is a positive. The negatives are going to cancel here. We are going to end up with 2 times 1 minus x squared to the negative second power times x, or 2x over 1 minus x squared to the second power. All right, we're going to substitute this into our limit here. This is going to be 2x over 1 minus x squared squared. All right, now that we've differentiated the first term in the numerator, we're going to differentiate this part of the numerator here, this beta times cos x minus x sine x. The derivative of cosine is negative sine, so we have negative sine x. And then to differentiate this x sine x, we're going to apply the product rule. The derivative of x is 1 times sine x gives us this first term here, which is sine x. And then we're going to add to that the derivative of sine x times x, the derivative of cosine x. So the other term here is going to be x cosine x. And in terms of the denominator, we're going to end up with 6x because that's the derivative of 3x squared. Now, the following step, I just rewrote and simplified what we had in the previous step. The alpha over 2 times 2x over 1 minus x squared. Well, these 2's are going to cancel. So we end up with alpha x over 1 minus x squared squared. We're going to combine this negative sine x here. And then after we distribute this negative to both of these terms, we can combine this negative x sine x and then the negative sine x that we end up with here to get negative 2 sine x. And then the other term that's going to be in the numerator is this minus x cosine x, since it's all inside this beta. From here, if you just substitute 0 for x, you will end up with another indeterminate form. Won't go through all the steps, but that's the case. However, when you're working through a really complicated problem, problem with a lot of steps, you really try to think about ways to make things easier for yourself. If we have to use L'Hopital's rule, we can, but maybe the better option here would just be to try to simplify this expression to see what we end up with in order to save ourselves some work. So that's exactly what we're going to do. Specifically, what we're going to do is just break this fraction up into smaller fractions and separate things to see what we get. And when we do that, we end up with these fractions here. At this point, we can make a bit of simplifications. These x's here are going to cancel, so we can just get rid of them. And then we end up with alpha over 1 minus x squared squared over 6. And here, well, we have 2 over 6. That's the same as 1 over 3. I'm just going to place that 2 over 6 with just a 3 in the denominator, which means we have beta sine x over 3x. And then for the third term, well, these x's are going to cancel. Let's just knock these guys out right now. When we do that, we get beta cos x over 6. And now we can make a little bit more progress. This first term here is just going to simplify to alpha over 6 because we substitute 0 in this expression here, the 1 minus x squared squared. You're going to end up with just 1. Alpha over 1 over 6 is just alpha over 6. But now I want you to pay close attention to the other two terms we have. We have now beta over 3 times the limit as x approaches 0 of sine x over x. Now, all calculus classes, you learn right away that the limit of x approaches 0 of sine x over x is 1. Typically, you kind of just memorize this because this limit is pretty important. It comes up pretty frequently. But if you're familiar with L'Hopital's rule, which at this point, I hope you are, you can see that this limit is equal to 1 using L'Hopital's rule. Sine of 0 is 0, and the limit as x approaches 0 of x is 0, which means that this would be an indeterminate form. So if you take the derivative of the numerator and denominator, you end up with cosine x over 1. And that limit as x approaches 0 will be 1. In any case, this limit is equal to 1. And then for the third term here, the limit as x approaches 0 of cosine x. This limit is also going to be equal to 1, which means that this expression is equal to alpha over 6 minus beta over 3 minus beta over 6, which simplifies to, well, beta over 3 is 2 beta over 6. 2 beta over 6 minus beta over 6 is 3 beta over 6. This is alpha over 6 minus 3 beta over 6. And this is equal to 2. If you remember from way back in the beginning of the problem, this limit, our original limit, is equal to 2. Now, by multiplying both sides of this equation by 6, we get that alpha minus 3 beta is equal to 12. So applying L'Hopital's rule, this second time gave us a second equation, and we didn't have to apply L'Hopital's rule a third time, even though we could have. But I want you to recall that once we had applied L'Hopital's rule the first time, we ended up with this equation up here. This alpha plus 2 beta is equal to 0. Now we're going to need this. I'm going to say let's say this is like equation 1. And let's say this is equation 2. I'm going to write solve system of equations using equations 1 and 2. We end up with the following system. Alpha plus 2 beta is equal to 0, and alpha minus 3 beta is equal to 12. There are a few ways you can do this, but I'm just going to subtract the equation 2 from equation 1. Just subtract these equations, use elimination. That's going to get rid of this alpha. So we'll end up with an equation with just beta. So if we subtract these two equations, we get 2 beta minus negative 3 beta, and that's 5 beta. The alphas are going to cancel. This is going to be equal to negative 12. And then by dividing both sides by 5, you get that beta is equal to negative 12 over 5. That means that we can use this value of beta to find alpha, which substitute this value of beta into either equation 1 or 2. Doesn't matter. I'm going to use equation 1. It's going to be alpha plus 2 minus 12 over 5 is equal to 0. It's going to be alpha minus 24 over 5 is equal to 0. So alpha is equal to 24 over 5. But remember, we want to find alpha plus beta. We're almost there, but not quite. Still one more step. But fortunately, this is the easier step. Alpha plus beta is just 24 over 5 minus 12 over 5, which is 12 over 5, or 2.4. All right, we are done. Honestly, it's pretty brutal that a question like this is on an entrance exam. But from my understanding, this is an exam taken by the top students in India, so I suppose it makes sense. In any case, this was a long and involved problem. There are other solutions, but I just chose to cover this one to make sure the video wasn't too long. But if you want to bring up any alternative solutions, or if you have any other comments or suggestions, any feedback for me, please let me know in the comment section. And otherwise, I will see you next video. Bye now.